In the previous lecture, I described the basic theory of interference, what is difference between constructive and destructive interference, superposition principle, methods to find the resultant of two or more than two sinusoidal waves of same frequency and acting in the same direction at a point in space, what is condition for constructive and destructive interference in terms of path difference and phase difference, how the intensity of resultant wave vary with the phase difference of the interfering waves, what are the conditions to observe a stationary interference pattern, and how to get two coherent sources for interference by using division of wavefront and division of amplitude. And I also discussed some famous experimental setups which are used in laboratory to observe interference pattern based on division of wavefront, such as Young's double slits, Fresnel biprism and Fresnel double mirror experiment. Mostly in all undergraduate optics lab, Fresnel biprism experiment is performed. With the help of this experiment, wavelength of monochromatic light can be determined by measuring the fringe width with the help of a travelling microscope. I have given the expression of fringe width in the previous lecture. By measuring the required parameters experimentally with the help of this equation, wavelength can be determined. With the help of this experiment, it is also possible to determine thickness of a transparent plate. For this, the plate is introduced in the path of one of the interfering beams and resulting shift in the position of central bright fringe is measured with the help of a travelling microscope. The required expression I have already obtained in the previous lecture. Here it should be noted that with monochromatic light it is not possible to recognize the central bright fringe, but if we use white light, then central bright fringe will be white and few fringes adjacent to this will be colored. So, shift in central bright fringe on introducing the plate can be measured easily by using white light source. Now, I am going to describe the formation of interference pattern by division of amplitudes. In this case, the incident beam is divided into two portions by division of its amplitude by partial reflection and refraction by some optical devices. The two portions afterward recombine to produce interference effect. For example, if a plane wave falls on a thin film, then the wave reflected from the upper surface interferes with the wave reflected from the lower surface. The colors when shown by thin films of oil on water, by soap bubbles or by cracks in a piece of glass can be explained by the phenomena of interference of light by division of amplitude. Let us first consider the interference by a plane parallel film of refractive index mu and thickness T illuminated by a plane monochromatic light of wavelength lambda as shown in this figure. Suppose the light wave travelling along AB is incident on the upper surface GH of the film. Part of this wave will be reflected from the upper surface of film in the direction BR and remaining will be refracted in the direction BC. Upon arrival at C, part of this refracted wave will be reflected from surface IH in the direction CB1 and part refracted in the direction CT. At B1, the ray CB1 will be again divided. A continuation of this process yields two sets of parallel rays, one on each side of the film. In each of these sets, the intensity decreases rapidly from one ray to next. If the set of parallel reflected rays BR, B1 R1, B2 RT, etc. is collected by lens and focus at some point, constructive or destructive interference will be formed at this point depending on the phase difference between the consecutive waves. It is such interference that produces the colors of the thin films. In order to find the phase difference between these rays, we must first evaluate the difference in the optical path traversed by a pair of successive rays, such as BR and B1R1. Suppose B1D is perpendicular drawn from B1 on BR, therefore, optical path difference between the waves BR and B1R1 is given by BC plus CB1 in film minus BD in air. With the help of geometry, we can show that this path difference will be equal to 2 mu t cos theta. Therefore, phase difference delta will be equal to 2 pi by lambda into path difference, that is 2 pi by lambda into 2 mu t cos theta. If the film is optically denser than the surrounding media, then the wave BR originated by reflection from B, a point on the surface backed by a denser medium, that is film, will be differ in phase by pi from the incident wave. But the wave B1R1, which originates by reflection at C, a point on the surface backed by a rarer medium, will experience no sudden phase change. Thus, the total phase difference between waves BR and B1R1 becomes 2 pi by lambda into 2 mu t cos theta plus pi. Therefore, if 2 mu t cos theta will be equal to n plus half lambda, where n is integer, the wave BR and B1R1 interfere constructively, and they will interfere destructively if 2 mu t cos theta is equal to n lambda, where n is again integer. Like reflected waves, the transmitted waves CT, C1, T1, C2, T2, etc. also satisfy the conditions for interference because they originate from the same incident wave. Here CT and C1 T1 are obtained without any sudden phase change due to reflection. The phase difference between CT and C1 T1 is therefore only due to optical path difference. Similar to reflected waves, here also we can determine the path difference between CT and C1 T1 using basic geometry, and here also it comes out to be 2 mu t cos theta. So, the transmitted waves CT and C1 T1 will interfere constructively when 2 mu t cos theta is equal to n lambda, and destructively when 2 mu t cos theta is equal to n plus half lambda. Thus, the condition for constructive and destructive interference for transmitted waves CT and C1 T1 are just reverse of that of the reflected waves BR and B1 R1. Since the geometry is same, the path difference between waves B1 R1 and B2 R2 will be same as between waves BR and B1 R1. Since B1 R1 and B2 R2 originate only from the internal reflection, so there would not be phase difference of pi due to reflection. Now, if 2 mu t cos theta is equal to n lambda, waves B1 R1 and B2 R2 will be in phase, and same holds for all succeeding pairs. Therefore, under this condition waves BR and B1 R1 will be out of phase, but waves B1 R1, B2 R2, B3 R3 and so on will be in phase with each other. On the other hand, if 2 mu t cos theta is equal to n plus half lambda, waves B1 R1 will be in phase with BR, but B2 R2, B4 R4, B6 R6 and so on will be out of phase with B1 R1, B3 R3, B5 R5 so on. Since B1 R1 is more intense than B2 R2 and B3 R3 is more intense than B4 R4 and so on, these pairs cannot cancel each other and hence there will be maximum intensity. For the minima of intensity, wave B1 R1 is out of phase with wave BR, but BR has a considerably greater amplitude than B1 R1. So that these two will not completely annul each other, but if we add the amplitudes of the waves B1 R2, B2 R2, B3 R3, we find that the resultant amplitude is equal to the amplitude of the wave BR. Therefore, in case of minima there will be complete darkness. Thus, if the film is of such a thickness that the condition part difference is equal to n lambda is satisfied, the film will appear perfectly dark and when seen by reflected light. On the other hand, if the thickness of the film is such that part difference is equal to n plus half lambda, then the intensity of the film will be maximum when seen by reflected light. For the transmitted light, when film thickness is such that the condition delta part difference is equal to n plus half lambda is satisfied, the pair of transmitted wave CT and C1 T1, C2 T2 and C3 T3 etc. are in opposite phase and therefore interfere destructively in pair. So, the resultant intensity will be minimum. If the thickness of the film is such that part difference is equal to n lambda is satisfied, the transmitted waves CT, C1, T1, C2, T2 etc. are in phase with each other and therefore, they interfere constructively leading to maximum intensity in the transmitted light. So, when there is maximum intensity in the reflected light, there would be minimum intensity in the transmitted light and vice versa. Thus, based on the above discussions, it is concluded that when a plane parallel film is illuminated with parallel monochromatic light, that is theta is constant R over the film will have maxima or minima of brightness all over according as the optical path difference between the directly and the internally reflected waves is odd or even multiple of lambda by 2. Now, suppose the plane parallel thin film is illuminated with a parallel beam of white light. If you neglect the small variation in the angle of refraction with wavelengths, then light waves of different colors follow approximately the same path within the film. Therefore, the optical path difference 2 mu t cos theta will be approximately same for all the colors. Hence, the colors whose wavelengths satisfy the condition 2 mu t cos theta is equal to n lambda will be absent in the reflected beam, but they will be present in the transmitted beam. On the other hand, colors whose wavelengths satisfy the condition 2 mu t cos theta is equal to n plus half lambda will be present in the reflected beam, but practically absent in the transmitted beam. Consequently, the film will have a uniform coloration all over, but the resultant color of the film by reflected light will be exactly complementary to the resultant color by transmitted light. Furthermore, when film thickness T is much smaller than lambda, then 2 mu t cos theta is negligible in comparison to lambda. In this case, phase difference delta, which is equal to 2 pi by lambda into 2 mu t cos theta, will be 0 for all wavelengths. Therefore, the film will appear perfectly dark by reflected light even when it is illuminated with white light. On the other hand, it will appear white when seen by transmitted light. Now, let us consider a film in the shape of a thin wedge whose side form a small angle alpha as shown in this figure. Now, suppose this film is illuminated with plane monochromatic light waves. Here also the directly reflected wave BR and the internally reflected wave B1 R1 originate from the same incident wave propagating along AB, and hence they are capable of producing observable interference effects. Here the two interfering waves do not reach the eye along parallel path, but they appear to diverge from a point Q in the rear of the film. So, destructive or constructive interference occurs at the point Q, which is however virtual. If the two interfering waves BR and B1 R1 fall on lens, they will cross each other at a real point Q prime, the focus conjugate of Q. As a consequence, real reinforcement or destructive interference would occur at Q prime. Thus, Q will be the position where the interference fringe appears to be formed. From geometry, we can find the optical path difference delta between the waves BR and B1 R1, and this comes out to be 2 mu t cos theta plus alpha, where T is the thickness of film at the point B1. The path difference thus varies both on account of changing thickness as well as changing angle of incidence theta. Now, taking into account the abrupt phase change of pi due to reflection at B, the condition for constructive and destructive interference between waves VR and B1 R1 becomes 2 mu t cos theta plus alpha is equal to n plus half lambda for maxima and 2 mu t cos theta plus alpha is equal to n lambda for minima. If the wave shaped film is illuminated by a parallel beam of monochromatic light of wavelength lambda, the angle of incident theta will be same at every point of the film, and so also angle of refraction. So, in this case variation in the optical path difference will take place only due to variation in the thickness of the film T from point to point of the film. At the edge of the wedge film, since T is equal to 0, the film appears perfectly dark because the two interfering waves are pi out of phase. At a distance from the edge such that path difference is equal to lambda by 2, 3 lambda by 2, 5 lambda by 2 and so on, the film will be bright, while at a distance so that path difference is equal to lambda, 2 lambda, 3 lambda, 4 lambda and so on, the film will appear dark. Thus, as we proceed along the film in the direction of increasing film thickness, we shall encounter alternately dark and bright bands parallel to the edge of the film. Deviation from perfect plainness of the surface will be immediately obvious through the curvature of these bands, because any one band is the locus of constant thickness of the film. That is why such fringes are called fringes of constant thickness. It can be shown that for a small angle of incidence, that is cos theta nearly equal to 1, the fringe width beta, that is the separation between the two consecutive dark or bright fringes, is given by lambda upon 2 alpha mu, where alpha is the wedge angle and mu is the refractive index of the film. Now, let us consider that the wedge shaped thin film is illuminated with parallel beam of white light. If the thickness at the thin edge is very small in comparison of the wavelength of violet light, then at the edge a truly achromatic black fringe parallel to the edge will be seen when it is viewed by reflected light. Now, if we move along the film in the direction of increasing thickness, we will first reach a point where the thickness of the film is such that the condition of constructive interference is satisfied for violet color. because wavelength of this color is least in the visible spectrum. Therefore, a violet fringe is seen at this point. Proceeding still further, successively blue, green, yellow and red fringes will be observed. These fringes are called fringes of equal chromatic order. Beyond certain point, thickness of the film becomes so large that the condition of constructive interference is satisfied for two or more colors simultaneously, and therefore, a colored band due to overlapping of bright fringes of more than one colors will be seen. If we still move in the same direction, we shall arrive at a point where such overlapping of different colors produces uniform illumination. Now, let us consider that a thin parallel film is illuminated by using extended white source as shown in this figure. In this case, light from each point of the source gives rise to a pair of coherent waves on reflection from the film, and cos theta is not same for all of them. Each point of the film is also seen by light from different points of the extended source. If at points A, B, C, the condition 2 mu t cos theta 1 is equal to n 1 plus half lambda 1, 2 mu t cos theta 2 is equal to n 2 plus half lambda 2, and 2 mu t cos theta 3 is equal to n 3 plus half lambda 3 are satisfied respectively, we shall observe a bright band of lambda 1 at A, a bright band of lambda 2 at B, a bright band of lambda 3 at C, and so on. Thus, we shall observe a set of equal inclination colored bands. If the film is of variable thickness, we shall again observe a set of colored band, each being a locus of equal thickness of the film. The color of any particular region of the film changes if the eye is shifted to a new position. Now, light from other points of extended source is reflected from that particular region of the film at different angles to the eye. In effect, 2 mu t cos theta alters throughout the film, leading to change in colors exhibited by thin film. This clearly explains the origin of color exhibited by a thin film of oil on the surface of water, or color of soap bubbles by light reflected from the sky. It should be noted that bright colors will be seen only when film is extremely thin, that is up to few wavelengths thick. The colors become fed for thicker films, and for such cases the direction of incidence should be kept nearly normal. Otherwise, at other angles the directly and internally reflected coherent waves may get separated to such an extent that their wave front may not interfere each other, and they may get so far apart that only one wave enters the eye at a time, and so all colors effectively may vanish when viewed by naked eye. Now, let us discuss the classification of fringes. As we have discussed, when a thin film is illuminated by light, the resultant transmitted or reflected intensities will depend upon the phase difference delta between two consecutive transmitted or reflected waves, and the phase difference is given by 2 pi by lambda into 2 mu t cos theta. Since the value of the phase difference delta may be varied by varying theta or t or lambda, accordingly we can divide the interference fringes of thin films into 3 classes. If phase difference varies mainly due to variation of theta while t remains constant, then fringes are termed as fringes of equal inclination or Hedinger fringes. If phase difference varies with variation in thickness T of the film, then fringes are called fringes of equal thickness or Fizeau fringes. Now, if the phase difference varies with variation in lambda, then the fringes are known as fringes of equal chromatic order or FICO fringes. The term FICO was used by Professor S. Tolansky. Now, in this lecture, I will describe some of the experimental setup used in laboratory to observe the fringes of equal thickness and fringes of equal inclinations. One of the most important experiment which is based on the division of amplitude is Newton ring experiment. In this experiment, a thin air film of progressively increasing thickness in all directions from one point can be formed by placing a plano-convex lens of large radius of curvature on a plain glass plate such that its convex surface faces the plate. The air film thus formed possesses a radial symmetry about the point of contact, and when it is illuminated normally with monochromatic light, the observed interference fringes are circular ring concentric with the point of contact. These rings are known as Newton's ring. The experimental arrangement to observe the Newton rings in laboratory is shown in this figure. Here A is a plano-convex lens placed on the glass plate B. The glass plate G reflects the light down so that it is incident normally on the plates. After reflection, it is transmitted through G and observed in the travelling microscope. If the film enclosed between the lens and the plain glass plate is extremely thin, then wedge angle alpha can be neglected as compared to angle of incidence theta. So, for normal incidence, the optical path difference between the two consecutive reflected waves becomes 2 mu times t. Thus, for this case, the condition for constructive and destructive interference for two consecutive reflected waves are given by 2 mu t is equal to n lambda for minima and 2 mu t is equal to n plus half lambda for maxima, where mu is the refractive index of the film and t the thickness of the film. For air film, mu will be equal to 1. As we know, an interference fringe of a given order n is the locus of the points of constant optical path difference. A dark fringe of the order n is the locus of those points where the film thickness T is n lambda upon 2 mu. Since the film enclosed between the convex surface and the plane surface possesses radial symmetry about the point of contact, the dark fringe will be circular in shape. So, here we will observe concentric bright and dark circular fringes as shown in this figure. It can be shown that the square of radius of dark ring of nth order is equal to n lambda r divided by mu, and square of radius of bright ring of nth order is equal to n plus half lambda r upon mu, where r is the radius of curvature of the convex surface. Thus, when Newton rings are observed by reflected light, the diameter of the bright rings are proportional to the square root of the odd natural numbers like 1, 3, 5, 7, so on, whereas the diameters of dark rings are proportional to the square root of natural number 1, 2, 3, 4 and so on. It can be shown that the rings gradually become closer as their radii increase as shown in this figure. Since t is equal to 0 at the point of contact of the lens and the glass plate. At this point, phase difference between the waves reflected from the upper and lower surfaces will be pi. Therefore, for the reflected light in the interference pattern, the central spot appears dark, but if it is seen in the transmitted light, the central spot will be bright. Now, I will discuss some important application of Newton ring experiment. One example of is the determination of the wavelength of the monochromatic light used. So, for this purpose we have to measure the diameter of the Newton rings with the help of the travelling microscope, and by using the relations lambda is equal to d n plus p square minus d n square upon 4 p r, where d n plus p square minus d n square is the difference of the squares of the diameter of n plus pth and nth dark rings, and r is the radius of curvature of the lens. With the help of Newton ring experiment, it is also possible to determine the refractive index of a given liquid. For this purpose also we have to measure the diameters of the Newton rings with air film as well as by introducing the liquid between the glass plate and convex lens, and by using the expression d n plus p square minus d n square for air divided by d n plus p square minus d n square for film, we can determine the refractive index of the liquid. We can, so with the help of Newton ring experiment, we can determine the wavelength of the monochromatic light used, and we can also measure the refractive index of a given liquid. Only thing is that we have to determine the diameter of the Newton rings precisely by using the travelling microscopes. Now, I will discuss another important experimental setup, which is based on division of amplitude. This is known as the Michelson interferometer. The main optical part of this interferometer consists of two highly polished plane mirrors M1 and M2 and two plane parallel glass plates G1 and G2 of equal thickness as shown here in the figure. The mirror M2 is fixed while M1 can be moved such that during the motion it remains exactly parallel to its preceding position. Normally, the rear side of the plate G1 is lightly silvered, so that the light coming from source S is divided into a reflected beam 1 and a transmitted beam 2 of equal intensity. The beams 1 and 2 are reflected back from mirrors M1 and M2 as shown in this figure respectively. The reflected beam 1 is transmitted through G1 along AE and reflected beam 2 is reflected from G1 along AE. These two waves travelling along AE are derived from the same source by division of amplitude. So, they will satisfy the condition of interference, and hence interference fringes can be observed by looking into mirror M1 through G1 from position E, provided proper adjustments are made. Here the glass plate G2 is called compensating plate. Its purpose is to equalize the total optical path of the beam reflected from M1 and the total path of the corresponding beam reflected from M2. This is essential when white light is used, but not for monochromatic light. In the Michelson interferometer, fringes of various forms such as straight lines, circles, parabolas, ellipses or hyperbolas can be observed depending upon the angle between the mirrors M1 and M2. But in the laboratory, the interferometer is adjusted for circular fringes for various applications. Therefore, here I will discuss the formation of circular fringes in the Michelson interferometer. To obtain the circular fringes, the mirrors M1 and M2 are made exactly perpendicular to each other with the help of screws attached with the mirrors, and to see good quality fringe, extended light source is used. An extended source may be obtained by placing a ground glass screen in front of the source of monochromatic light. The origin of circular fringes can be understood with the help of this diagram. Here M2 prime is the virtual image of M2 formed by reflection in G1. We can also think the extended source as being L behind the observer and forming two virtual images L1 and L2 in M1 and M2 prime respectively. These virtual sources are coherent if T is the separation between M1 and M2 prime. The virtual sources will be separated by 2T. When T is exactly an integral number of half wavelengths, that is the path difference 2T is equal to an integral number of whole wavelengths, all rays of light reflected normal to the mirrors will be in phase. Rays of light reflected at an angle, however, will in general not be in phase. The path difference between the two rays coming to the eye from corresponding points P prime and P double prime is 2T cos theta as shown here in the figure. The angle theta is necessarily the same for the two rays when M1 is parallel to M2 prime, so that the rays are parallel. Hence, when the eye is focused to receive parallel rays, the rays will reinforce each other to produce maxima for those angle theta satisfying the condition 2T cos theta is equal to n lambda. Since for a given n lambda and t the angle theta is constant, the maxima will lie in the form of circles about the foot of the perpendicular from the eye to the mirrors. Fringes of this kind, when parallel beam are brought to interfere with a phase difference determined by angle of inclination theta, are called fringes of equal inclination. In this figure, effect of changing T on the fringe pattern is shown. When M1 is moved slowly towards M2 prime, so that T is decreased, then the radius of a given ring characterized by a given value of order n must decrease, because the product 2T cos theta must remain constant. The rings therefore shrink and vanish at the center, a ring disappearing each time T decreases by lambda by 2. This follows from the fact that at the center cos theta is equal to 1, then 2T is equal to n lambda. So, the change n by unity T must change by lambda by 2. Now, as M1 approaches M2 primes, the rings become more widely spaced until finally we reach a critical position where the central fringe has spread out to cover the whole field of view. This happens when M1 and M2 prime are exactly coincident, that is T is equal to 0, because under this condition the path difference is 0 for all angles of incidence. If the mirror M1 is moved still farther, it effectively passes through M2 prime and new widely spaced fringes appear, growing out from the center. These will gradually become more closely spaced as the path difference increases. Now, I will describe some of the applications of Michelson interferometer. One important application of this interferometer is the measurement of wavelength of monochromatic light. For the measurement of wavelength, concentric circular fringes are invariably used. So, first M2 is adjusted perpendicular to M1 to get concentric circular fringes. Now, suppose the separation between M2 prime and M1 is such that a bright fringe of the order M is formed in the center of the field of view. We therefore have for the central bright fringe 2t is equal to n lambda, since cos theta will be equal to 1. Now, we move M1 such that t increases by lambda by 2. In this case, the path difference between the normally reflected waves from the center of field becomes 2 into t plus lambda by 2, and therefore, now we have 2 t plus lambda by 2 equal to m plus 1 lambda. That is, the condition of constructive interference is again satisfied at the center of field, but the new bright fringe now is of the order m plus 1 instead of m. We therefore conclude that each time t is increased by lambda by 2 in the field of view where a particular bright fringe originally appeared, the neighboring bright fringe of next higher order shall be visible. That is, there will be a lateral shift of one fringe in the field of view. Therefore, for the displacement of n bright fringes in the center of field, M1 must be moved through n lambda by 2. Thus, to determine lambda, the mirror M1 is moved from one position corresponding to micrometer reading x1 to another position corresponding to micrometer reading x2, and the number n of the bright monochromatic fringes which cross the center of the field is counted. So, on the basis of above argument, we can write the relation n lambda by 2 equal to x2 minus x1. From this relation, we can compute the value of lambda by measuring x2 minus x1s. Another important application of Michelson interferometer is the determination of difference between the wavelength of sodium D lines. Sodium light contains two very close wavelengths which are known as D1 of wavelength 5896 angstrom and D2 lines of wavelength 5890 angstrom. The difference in lambda 1 and lambda 2 can be precisely determined with the help of Michelson interferometer. So, now I will discuss how this is done in this interferometer. Suppose for a particular position of M1 at the central field of view, the condition 2t is equal to n1 lambda 1 and 2t is equal to n2 lambda 2 are satisfied simultaneously, where lambda 1 and lambda 2 are the wavelengths of D1 and D2 line of sodium respectively. In this case, bright ring of order n1 of wavelength lambda 1 practically coincides with the bright ring of order n2 of wavelength lambda 2, leading to maximum visibility at the center. Due to difference in lambda 1 and lambda 2, as the separation between M1 and M2 prime gradually increases, the maxima at first fall further and further from coinciding. Ultimately, at a particular separation, the maxima of one practically coincides with the minima of other wavelengths and vice versa, thereby producing minimum visibility. This happens when the extra path difference introduced at the center due to motion of M1 contains one half wavelength more of radiation lambda 2 than that of the other. Continuing the motion of M1 in the same direction again gradually brings the maxima of two patterns close together. Ultimately, they again coincide at the center when the extra optical path difference 2 T naught introduced at the center contains one more wavelength of one radiation than of the other. The visibility of the fringes is again maximum, and the conditions 2 T plus T naught is equal to N 1 plus capital N lambda 1 and 2 T plus T naught is equal to N 1 plus capital N plus 1 lambda 2 will be satisfied. Here it has been assumed that lambda 1 is greater than lambda 2 and T naught is the displacement of M 1 between successive visibility of maxima, and capital N represent the number of bright fringes of wavelength lambda 1 emerging at the center due to displacement T naught of mirror M 1. Therefore, we can also write 2 T naught is equal to capital N lambda 1 and 2 T naught is equal to capital N plus 1 lambda 2. From these two equations, we can write lambda 1 by lambda 2 is equal to N plus 1 divided by N. Here it is very difficult to count N, but N can be determined from the relation capital N is equal to 2 T naught divided by lambda 1. Using this, we can write lambda 1 minus lambda 2 divided by lambda 2 equal to 1 over capital N, which is equal to lambda 1 divided by 2 T naught. Finally, from this we can write lambda 1 minus lambda 2 equal to lambda 1 into lambda 2 divided by 2 T naught, which will be nearly equal to lambda average square divided by 2 T naught, where lambda average is the average of lambda 1 and lambda 2. Thus, by measuring the positions of M 1 for two successive visibility maxima in the central field of view, lambda 1 minus lambda 2 can be determined. Since visibility minima can be distinguished more accurately than the maxima, the value of T naught is therefore determined by the position of M 1 for two successive minimum visibility position. Further, in order to minimize the errors, normally the position of mirror M 1 is noted for 10 successive visibility minima, and from this the separation between value of T naught can be determined more accurately. Now, I will discuss another important interferometer, which is known as the Fabry-Perot interferometer. In this interferometer, the interference fringes are produced in the transmitted light after multiple reflections in the air film between two plain glass plates thinly silvered on the inner surfaces, as shown in this figure. To observe the fringes, a broad source of monochromatic light is used. Suppose a ray from the point P1 on the extended source is incident at the angle theta. This will produce a series of parallel transmitted rays at the same angle, which may be brought together at the point P2 on the screen EF with the help of a lens. The condition for reinforcement of the transmitted rays is 2T cos theta is equal to m lambda, where m is integer, for air film of thickness T. This condition will be fulfilled by all points on the circle through P2 with their center at O. The intersection of the axis of the lens with the screen EF. When the angle theta is decreased, the cosine will increase until another maxima is reached, for which m is greater by 1, 2, 3 and so on. So that we have for the maxima a series of concentric rings on the screen with O their center. These rings are known as fringes of equal inclination. In this case, effect of changing T on circular fringes is same as we have discussed for Michelson interferometer. In this in the interferometer used in the laboratory, one plate is fixed while the other may be moved in both directions, keeping parallel to its preceding position to change the value of T. This interferometer is also used for the measurement of wavelength of monochromatic light and difference in wavelengths of sodium D1 and D2 lines. The methods are same as described above for the Michelson interferometers. So, let me summarize what I have discussed in these lectures. So, in this lecture I have discussed how to get interference pattern by division of amplitude by taking example of thin parallel films of constant thickness as well as taking the film of variable thickness, and I also discuss how this colored effect is observed through thin films, and I discuss 3 important experiments which are usually performed in the laboratory like Newton ring experiment, Michelson interferometer and the Fabry-Perot interferometer, and how to determine the wavelength of monochromatic light by using these experimental setups. Thank you.